The next AI breakthrough may depend less on a clever paper than on a substation. That sounds like a joke until you follow the chain. A model needs chips. The chips need high-bandwidth memory. The memory needs advanced packaging. The package needs a foundry slot. The rack needs networking, power delivery, and cooling. The building needs land, transformers, water strategy, construction crews, permits, and a grid connection. And the whole thing needs capital, lots of it, spent years before the product earns $1. So this is not just a story about bigger models. It is a story about the physical world catching up with software. This is depth and signal. Today, we are looking at the power behind AI. Why the model war is becoming an infrastructure war. Why the stock market is trying to price that shift. And why the value may be moving from the AI service you see on screen to the machinery underneath it. The central question is simple. If AI services become easier to copy, where does the scarce value go? One answer is down the stack, into chips, data centers, electricity, cooling, permits, and the balance sheet's big enough to secure all of it. For most users, AI still feels like software. You type into a box, you get a response. Maybe it writes code, summarizes a document, drafts an email, turns a sketch into an image, or argues with your spreadsheet in a tone that is somehow both confident and slightly too cheerful. On the surface, the product is light: a chat window, a button, a copilot, an API call. But underneath that surface, the product is getting heavier. Epoch AI's paper on trends in AI supercomputers puts numbers on that shift. The researchers built a dataset of 500 AI supercomputers from 2019 to 2025. Their finding is blunt. The performance of the leading systems doubled about every 9 months. Hardware acquisition cost and power needs roughly doubled every year. Those are not normal software company curves. Those are industrial curves. The paper estimates that xAI's Colossus system, as of March 2025, used about 200,000 AI chips, cost roughly $7 billion in hardware, and required about 300 megawatts of power. That is a research estimate, not a company-confirmed line item. But as an order of magnitude signal, it tells you what has changed. Frontier AI is no longer just a race to write better code. It is a race to assemble, power, cool, and finance machines so large that the machine itself becomes the strategy. And if the same scaling trend continued to 2030, the Epoch paper estimates the leading system would need about 2 million AI chips, more than $200 billion of hardware, and about 9 gigawatts of power. That is not a prediction to carve into stone. It is an extrapolation. It is the paper saying, if this curve does not bend, the physical world becomes the bottleneck. That matters because the old mental model of software starts to break. In the old model, the scarce thing was code. Distribution mattered, yes. Data mattered, yes. But once the software existed, the marginal cost of another user was often close to magic. Not zero, but low enough that software could scale like software. Frontier AI does not behave that cleanly. Every generated answer has a compute cost. Every better model increases pressure somewhere in the stack. If a product becomes agentic, meaning it does not just answer one prompt, but plans, checks, retries, calls tools, and runs in the background, then inference is no longer a little moment after training. It becomes a continuous operating load. That is the important shift. Training is the spectacular part. Inference is the business. Training creates the model. Inference serves the model all day to users, workflows, agents, searches, recommendations, coding tools, ad systems, customer support bots, and whatever else gets stuffed behind a sparkle icon this quarter. NVIDIA has a very self-interested phrase for this. It calls modern data centers AI factories. The phrase is marketing, so we should not swallow it whole. But it is also useful because it points at something real. A factory converts inputs into outputs. In this case, the inputs are electricity, chips, memory, networks, cooling, land, and capital. The outputs are tokens, recommendations, ad rankings, code completions, synthetic media, search answers, and cloud revenue. That is why NVIDIA's own filings no longer describe the data center as just a room full of servers. They describe a full rack-scale platform: GPUs, CPUs, networking, switches, systems, software stacks, power delivery, and cooling. The data center is becoming the unit of computing, and the financial numbers show the same thing. NVIDIA reported $215.9 billion of revenue in fiscal 2026, up 65% year over year. Its data center revenue was $193.7 billion. That is not a side business. That is the center of gravity. The same logic is showing up across the rest of the stack. TSMC, the foundry behind many of the most advanced chips, said high-performance computing was 61% of its revenue in the first quarter of 2026. The hyperscalers are talking less like software companies and more like utilities, builders, and industrial planners. They talk about power capacity, liquid cooling, leases, construction commitments, supply agreements, and future infrastructure obligations. So the first act of this story is not AI is getting expensive. That is true, but too small. The real story is that AI is becoming physical. And once AI becomes physical, the competitive advantage changes. A company with a good model but no capacity may lose to a company with a slightly worse model and cheaper, more available inference. A startup with a brilliant agent may still depend on cloud prices set by a few infrastructure owners. A product team may discover that latency, region availability, and compute allocation matter as much as model benchmarks. This is where the user's experience and the capital stack meet. The chat box looks weightless. The answer is not. That is why the next AI cycle may reward the companies that control the substrate, not only the companies that ship the most charming demo. And that brings us to the first toll road. Before we get there, hold on to one distinction. There is a difference between the AI product and the AI capacity behind it. The product is what gets copied: a sidebar assistant, a document summarizer, a coding agent, a meeting note taker, a search answer. Once users understand the pattern, competitors can often imitate the interface, maybe not perfectly and not with the same model quality, but enough that the feature starts to feel expected. Capacity is harder to copy. Capacity is the right chips in the right place, with the right power contract, with the right cooling, with the right software stack available at the right price. That is not a weekend feature sprint. That is a multi-year position. This is the heart of the infrastructure thesis. If AI becomes a standard layer in software, the visible service may become more commoditized. The invisible capacity may become more strategic. When people say AI chips, they usually mean GPUs. That is understandable. NVIDIA became the main character of the AI infrastructure story for a reason. In fiscal 2026, NVIDIA's data center revenue reached $193.7 billion. Data center compute revenue grew 59%, and data center networking revenue grew 142%, driven by the ramp of NVLink compute fabric for Blackwell systems. That networking number matters. It tells you the chip is not enough. The modern AI system is not one heroic processor sitting alone under a spotlight. It is a dense machine made of accelerators, CPUs, high-bandwidth memory, network switches, optical links, power delivery, cooling loops, software, and scheduling systems that try to make thousands of chips behave like one computer. The toll road has many toll booths. Start with the accelerator. GPUs, custom ASICs, TPUs, Trainium, MTIA, whatever the platform owner calls its silicon. Then add HBM, high bandwidth memory, because moving data fast enough is part of the problem. Then add advanced packaging, because the chip and memory need to sit close enough together to behave like a system. Then add the foundry capacity to make the advanced logic. Then add networking, because a model training run or large inference cluster is only as good as the fabric connecting the nodes. Then add power and cooling, because a rack-scale AI system is not polite about electricity. This is why just build your own chip is a much smaller sentence than the reality behind it. Custom silicon can be strategically important. It can lower inference cost. It can reduce dependency on one vendor. It can give a cloud provider better margins on its own workloads, but it does not make the rest of the stack vanish. You still need a foundry. You still need packaging. You still need memory. You still need compilers and software. You still need enough volume for the economics to work. And you still need customers to move workloads onto the thing. This is where TSMC becomes central. In the first quarter of 2026, TSMC reported net revenue of 1.134 trillion new Taiwan dollars, up 35.1% year-over-year. Its gross margin was 66.2%. Its operating margin was 58.1%. And high-performance computing accounted for 61% of revenue. TSMC management told investors that its 2026 capital budget was expected toward the high end of its $52 to $56 billion range, citing robust HPC and AI demand. That is the foundry layer telling the same story as the model layer. The demand is not abstract. It is showing up in wafer capacity, advanced nodes, and packaging. TSMC said its N2 process entered high-volume manufacturing in the fourth quarter of 2025, with demand supported by smartphone and HPC/AI applications. It also said it was expanding N3 capacity to meet strong AI demand, including new fab plans and tool conversion. But here is the part that should slow down every clean narrative. Foundry capacity does not appear because a CEO says scale on an earnings call. TSMC's management put it plainly. It takes 2 to 3 years to build a new fab and another 1 to 2 years to ramp it. No shortcuts. That is a sentence worth keeping. No shortcuts. In software, a great team can sometimes compress time. In semiconductors, physics and construction get a vote. So do tools, materials, labor, yields, packaging capacity, power supply, and customer qualification. And advanced packaging is now one of the pressure points. TSMC said advanced packaging capacity remains tight. It pointed to large reticle CoWoS as the current main supply approach, while it works on CoPoS. That sounds obscure until you translate it. The AI chip is not just a chip. It is an assembled system of compute and memory that has to be physically packaged at extreme density. If the packaging bottleneck is tight, the chip supply is tight, even if wafers exist. This is why the infrastructure story cannot be reduced to NVIDIA versus custom chips. The real question is, who controls scarce throughput across the full path from design to deployed rack? NVIDIA says Blackwell Ultra delivers 50 times higher throughput and 35 times lower token cost than Hopper. It also says Vera Rubin is designed to deliver up to 10 times lower token cost versus Blackwell. Those are vendor claims. They belong in the script as vendor claims, not independent truth. But even if you haircut the marketing, The direction is clear. The industry is optimizing for token economics, not just benchmark performance. Token economics. How many useful answers can you produce per dollar, per watt, per rack, per megawatt, per region, per unit of scarce capacity? That is where the model race becomes the infrastructure race. If two AI assistants feel similar to users, the winner may be the one that can serve the answer cheaper, faster, and more reliably. If every enterprise wants agents running all day, the bottleneck is not just model quality, it is the cost of continuous inference. If a cloud provider can move a meaningful share of inference onto its own chip, it may gain margin leverage. If it cannot, it keeps paying the toll. This also explains the awkward middle ground for labs building or partnering on chips. They may not be escaping NVIDIA. They may be diversifying around NVIDIA. That is less dramatic, but more accurate. The strongest AI companies are not trying to live in a world with one supplier, one foundry node, one packaging path, one memory supplier, one cloud region, or one power strategy. They are trying to buy options, because in this market, optionality is capacity, and capacity is strategy. This is also why the phrase AI hardware war can be misleading if it sounds like one clean battle. There are really several battles stacked together. There is the accelerator battle, who supplies the GPUs and custom chips. There is the memory battle, who can deliver enough high-bandwidth memory. There is the packaging battle, who can assemble compute and memory at the required density. There is the networking battle, who can move data through the cluster fast enough. There is the software battle, who can make the hardware usable by developers. And there is the procurement battle, who can reserve supply early enough that their roadmap is not held hostage by everyone else's demand. The companies that win one layer do not automatically win all of them. That is why the most useful picture is not a single chip. It is a bottleneck chain. And right now, the chain is tight enough that every link has pricing power, strategic value, or both. Once the chip exists, it still has to live somewhere. That somewhere is becoming one of the most expensive parts of the AI economy. The term data center used to sound almost passive. A place where data sits, a warehouse for servers, a background cost of the internet. That is not the right mental model anymore. The AI data center is closer to a factory. It takes inputs and produces economic output. It needs land, buildings, racks, networking, power systems, cooling, security, maintenance, software, and a customer pipeline that can turn capacity into revenue before the depreciation clock gets too loud. The hyperscalers are already describing it this way, even when they do not use the word factory. Microsoft said Azure surpassed $75 billion in annual revenue, up 34%. It said it operates more than 400 data centers in 70 regions. It also said it added more than 2 gigawatts of new capacity in fiscal 2025, and that every Azure region is AI first and can support liquid cooling. That is a software company talking like an infrastructure operator. The balance sheet makes it clearer. Microsoft's annual report lists property and equipment at cost of $298.6 billion as of June 30, 2025, up from $212.0 billion a year earlier. Net property and equipment rose to $205.0 billion from $135.6 billion. Microsoft also disclosed $32.1 billion of commitments for construction of new buildings, building improvements, and leasehold improvements, primarily related to data centers. And it had $92.7 billion of additional leases, primarily for data centers, that had not yet commenced. This is not an app update. This is a construction cycle, Amazon tells the story even more directly. It reported cash capital expenditures of $128.3 billion in 2025, up from $77.7 billion in 2024. Those expenditures primarily reflected investments in technology infrastructure, the majority supporting AWS growth, plus fulfillment capacity. In its shareholder letter, Amazon described the cash cycle of AWS in unusually plain terms. AWS has to lay out cash for land, power, buildings, chips, servers, and networking gear before it can monetize the capacity. Amazon said that can be 6 to 24 months before billing customers, depending on the component. That is the factory timeline. Cash first, revenue later. And the scale is large. Amazon said AWS added 3.9 gigawatts of new power capacity in 2025, expects to double total power capacity by the end of 2027, and has an AWS AI revenue run rate over $15 billion in the first quarter of 2026. Those are company statements, so we treat them as company statements, but they show how the cloud providers are thinking. Power capacity is now a growth metric. Meta is on the same path. Its Q1 2026 investor deck showed capital expenditures of $19.84 billion for the quarter. Its 2025 annual capex was $72.215 billion. On the Q1 2026 call, Meta said capex was driven by servers, data centers, and network infrastructure. Then it raised its 2026 capex guidance to a range of $125 to $145 billion, up from the prior $115 to $135 billion range. The explanation? Higher component pricing and additional data center costs to support future capacity. Meta also said, compute is becoming increasingly important because it determines the quality of the services it can deliver. That sentence is a quiet admission of the new product logic. The quality of the app is tied to the depth of the infrastructure. Alphabet is similar. In the first quarter of 2026, it spent $35.7 billion on capital expenditures, primarily technical infrastructure. It said it expects to significantly increase 2026 investment in technical infrastructure, including servers, network equipment, and data centers, relative to 2025. Alphabet also reported $75.6 billion of future lease payments for leases primarily related to data centers that had not yet commenced, and it disclosed $232.7 billion of expected future fixed or minimum guaranteed commitments under long-term supply agreements, energy service agreements, and content agreements. Now, a caveat. Not all of this is pure AI capex. The companies do not always separate AI infrastructure from cloud, search, ads, video, enterprise services, fulfillment, or general technical infrastructure. So the honest phrase is often AI and cloud infrastructure, not AI alone. But that caveat does not weaken the thesis. It sharpens it. AI is becoming embedded inside the entire compute base. Search needs it. Ads need it. Cloud customers need it. Agents need it. Recommender systems need it. Coding tools need it. Customer support needs it. The boundary between AI infrastructure and normal infrastructure is getting blurry because AI is becoming normal infrastructure. That is the paradigm shift. The user sees a feature. The company sees a multi-year asset base. And the market sees a question. Will this capacity earn enough to justify the spend? That is not guaranteed. CapEx can be productive, or it can become a drag. If demand disappoints, if pricing falls, if models become more efficient, if competitors overbuild, if electricity becomes constrained, if depreciation rises faster than revenue, the factory can hurt margins. This is why the market signal matters, but we are not there yet. First, we need to talk about the input that does not care about software roadmaps. Electricity. One more point before the grid. The factory model changes how we should read product announcements. When a company says it is launching a more powerful assistant, the obvious question is model quality. Is it smarter? Does it reason better? Does it use tools? Does it remember context? Fine questions. But the infrastructure question is different. Can the company serve that assistant to hundreds of millions of users without crushing margins? Can it offer premium tiers without running into capacity limits? Can it put the model in enterprise regions where customers need data controls? Can it make the experience fast enough that users trust it for daily work? Can it absorb a usage spike when the feature actually becomes popular? Those questions are not answered in a demo. They are answered in CapEx, leases, power capacity, and operating discipline. There are two kinds of power in this story. The first is energy over time. That is measured in terawatt hours. It tells you how much electricity a system consumes across a year. The second is power at a place. That is measured in gigawatts or megawatts. It tells you how much supply you need at a specific moment, at a specific location, through real wires, substations, and transformers. AI data centers need both. They need the annual energy, and they need a large enough pipe into the site. That distinction matters because the grid is not a spreadsheet. You cannot just say, the country has electricity, and assume a hyperscale facility can plug in wherever the land is cheap. The power has to be available where the data center is, when it needs it, at the reliability level the operator requires. This is where the AI story becomes very concrete. Lawrence Berkeley National Laboratory's 2024 U.S. Data Center Energy Usage Report estimated that U.S. data centers consumed 176 terawatt-hours of electricity in 2023. That was 4.4% of total U.S. electricity consumption. The same report projected that by 2028, U.S. data center electricity use could reach roughly 325 to 580 terawatt-hours. In power terms, that is 74 to 132 gigawatts of demand. In share terms, 6.7 to 12.0% of forecast U.S. electricity consumption. Then, the 2025 update moved the timeline forward. It estimated 2024 U.S. data center electricity use at 192 terawatt-hours, or 4.7% of total U.S. electricity. Its reference case for 2030 is 649 terawatt-hours, or 11.8% of forecasted U.S. electricity use. With compounded uncertainty, the range is 521 to 843 terawatt-hours, or 9.5 to 15.3% of total U.S. electricity. That range is wide for a reason. The future depends on equipment shipments, GPU and ASIC mix, server lifetimes, utilization, power draw, cooling, power usage effectiveness, inference demand, regional siting, and the speed of efficiency improvements. So the right takeaway is not one magic number. The right takeaway is that the uncertainty itself is strategic. Think about the difference this way. If a normal software product is more popular than expected, the company has a scaling problem. That can be painful, but the default answer is usually more cloud capacity, more optimization, and a higher bill. If an AI infrastructure plan is wrong by enough, the answer may not be available on the same timeline. You may need more accelerators that are already allocated, more transformers with long lead times, more power in a region where the queue is full, more cooling in a climate where water is politically sensitive, more building capacity in a county that just discovered what a hyperscale data center sounds like. The constraint is not only cost, it is time. If you are a cloud provider, you are making multi-year commitments under uncertain demand. If you are a utility, you are planning generation and transmission under uncertain load growth. If you are a regulator, you are trying to decide who pays for upgrades before anyone knows exactly how big the bill becomes. If you are a community, you are being asked to accept land use, water use, noise, and power demand for an industry that still changes product names every few months. That is not easy governance. It is also not just a climate story, though climate matters. It is a reliability story, an affordability story, a timing story, and a location story. The speed mismatch is brutal. A model can improve in months. A data center can take years. A transmission upgrade can take longer. A power plant can take longer still. Transformers and gas turbines have their own bottlenecks. Permitting has its own clock. Local politics has its own clock. Software wants to scale instantly. The grid politely declines. Amazon's own framing shows the business pressure. AWS said it added 3.9 gigawatts of new power capacity in 2025 and expects to double total power capacity by the end of 2027. Again, company statement. But it tells you that power is no longer back-office plumbing. It is a growth input, and federal regulators are now reacting to that pressure. AP reported in June 2026 that the Federal Energy Regulatory Commission directed 6 regional grid operators to help AI data centers and other large power users connect to the transmission system in a timely and orderly manner. AP also reported that under the order, data centers would pay the full cost of grid upgrades needed for their connection. That detail matters, because the fight is not only can the data center connect, it is who pays when it does. If a data center needs a transmission upgrade, should the cost sit with the developer, the utility, all ratepayers, or some combination? If the data center gets priority access, what happens to residential bills, factories, hospitals, and small businesses? If the data center brings its own power, what happens to emissions goals and local air quality? If it waits for clean power, what happens to the AI company's deployment schedule? These are not abstract policy questions anymore. They are becoming product questions. If one cloud region has cheap, abundant power, and another has grid constraints, model availability and price may diverge. If a company can put flexible workloads where power is available, it may gain an advantage. If a data center can pause or shift non-urgent workloads during grid stress, it may become easier to permit. But for this pilot, that stays a caveat, not a new section. The main point is simpler. The bottleneck chain has moved beyond chips. It now includes substations. And once the bottleneck includes substations, policy enters the stack. This is where the energy conversation often gets too simple. Some people want to make it only about emissions. Some want to make it only about national competitiveness. Some want to make it only about consumer bills. Some want to make it only about local jobs. The uncomfortable part is that all of those are real. AI data centers can support economically important services and still create local energy stress. Clean power goals can be important and still run into timing constraints. Utilities can need new investment and still shift costs unfairly if regulators are not careful. Companies can make credible sustainability commitments and still need firm power at hours when wind or solar are not enough. This is why the grid is not a footnote. It is where the competing promises of the AI boom meet the physical limits of the energy system. AI infrastructure does not stop at the fence around the data center. It has to pass through federal transmission policy, state utility regulation, local zoning, water rules, clean energy mandates, tax incentives, community opposition, and arguments over who pays for grid upgrades. This is where the phrase, the stack, gets bigger. In software, the stack might mean model, database, cloud provider, front-end, and API. In AI infrastructure, The stack now includes regulators, mayors, county boards, utility commissions, environmental rules, and neighbors who would rather not live next to a building full of fans. This is not a side issue. It is a deployment constraint. AP reported that FERC's June 2026 action directed 6 regional grid operators to ensure large power users can connect to the transmission system in a timely and orderly manner, while leaving states in control of retail electric rates, terms, and conditions. AP also reported that grid operators were asked to respond within 30 days on adequate power supplies for new and future data centers, and within 60 days on plans to integrate large power users. That is the federal side trying to move faster, but local and state politics are moving too, sometimes in the opposite direction. AP reported that on July 14, 2026, New York's governor signed an executive order pausing state permitting for new large data centers for up to a year while regulators create standards addressing environmental impacts, energy demand, water usage, and other factors. Notice the wording there. AP reported. That is not a throwaway phrase. It is how we avoid turning a secondary report into more certainty than we have. The direction of the policy story is clear enough to discuss, but exact legal language belongs to the primary order. The broader pattern is still clear. States and localities are trying to decide whether AI data centers are economic development, energy risk, environmental burden, strategic infrastructure, or some inconvenient mix of all four. AP reported that similar moratoriums have been proposed in at least a dozen states, though most have not advanced, while some local governments have imposed temporary bans. It also reported clean energy requirements and regulatory moves in states such as Michigan, Oregon, Minnesota, and New York. The political tension is obvious. Data centers can bring investment, jobs, tax base, and strategic relevance. They can also bring power demand, water demand, noise, land use fights, and fears that households will subsidize infrastructure built for trillion-dollar companies. Both sides can have real points. That is what makes this a good depth and signal story. It is not data centers good or data centers bad. It is that the AI build-out has escaped the screen and arrived in places with existing power grids, existing water systems, existing politics, and existing bills. For AI companies, this means political permission becomes a form of capacity. The companies that can secure sites, negotiate utility arrangements, address community concerns, and absorb grid upgrade costs may move faster than companies with better demos but worse infrastructure execution. For cloud platforms, permitting can become a competitive advantage. A region with faster approvals and credible power supply can pull investment away from a region with opposition or uncertainty. For investors, local backlash is not just a reputational risk. It can delay revenue conversion. It can raise costs. It can redirect CapEx. It can change which utilities, builders, equipment suppliers, and regions benefit. And for communities, this is where AI becomes tangible. Not as a chatbot, as a utility bill, as a water use debate, as a noise complaint, as a zoning hearing, as a promise of jobs, as a promise that might or might not match the footprint. The skeptics read is important here. A moratorium in one state does not stop the national build-out. A FERC order does not create new generation overnight. A clean energy requirement does not automatically eliminate emissions if the accounting is weak or the grid mix is constrained. And a company promise about sustainability is still a company promise. But the direction is hard to miss. Permitting is no longer downstream of AI strategy. It is AI strategy. The model can be ready, the chips can be ordered, the building can be designed, and still the answer may be not until the grid, the regulator, and the community agree. That creates a different kind of moat, not a software moat, not a patent moat, not even a data moat, a permission moat. The ability to get a large site approved, powered, cooled, connected, and accepted may become as important as the ability to train the model. That sounds strange if you think AI lives in a browser tab. It sounds less strange if you think AI lives in a physical network of industrial assets. That leads to the final act, the market trying to decide who owns the bottleneck. This is the part where stock charts become tempting. Semiconductors are up. Power equipment is interesting. Utilities are suddenly part of AI conversations. Data center builders, cooling companies, networking suppliers, memory makers, foundries, cloud platforms, everyone gets pulled into the same narrative. But a stock chart is not proof. It is a pressure gauge. It tells you where investors believe the pressure is building. It does not tell you whether the trade is right. So, to be explicit, this is not investment advice. The point is not to say which stock should go up or down. The point is to understand how public markets are translating the AI build-out into categories of expected scarcity. A price chart can show attention. It can show expectation. It can show narrative heat. It cannot by itself prove durable value creation. So the sober way to treat market trends is category first. Not buy this. Not AI made this stock go up. The better framing is, investors have treated certain categories as exposed to AI infrastructure demand, and the filings show why that exposure exists. The direct evidence is not the price line. It is the CapEx, commitments, and revenue mix underneath it. NVIDIA data center revenue reached $193.7 billion in fiscal 2026. TSMC said HPC was 61% of its first quarter 2026 revenue. Amazon cash capital expenditures reached $128.3 billion in 2025. Meta raised its 2026 CapEx guidance to $125 to $145 billion. Alphabet spent $35.7 billion on CapEx in the first quarter of 2026. Microsoft disclosed $32.1 billion of construction commitments primarily related to data centers, plus $92.7 billion of not yet commenced leases primarily for data centers. That is the market signal with a source trail. The analyst layer adds color, but it needs a label. MarketWatch reported Morgan Stanley analyst Brian Nowak forecasting large U.S. tech capex around $1.2 trillion in 2027 and $1.4 trillion by 2028. It also reported a forecast for hyperscale compute capacity to quadruple to 120 gigawatts by 2028. That is analyst reporting. It is not company guidance. It should be treated as a view of market expectations, not a fact about the future. Business Insider also reported Morgan Stanley framing that data center protests and moratoria are becoming an emerging market risk with possible effects across power, construction, and AI infrastructure equities. Again, useful sentiment, not hard proof. The deeper point is the paradigm shift. If AI services become commodities, the scarce value may move toward infrastructure. Think about the product layer. More companies are adding AI assistants. More apps are getting agents. More enterprise tools are using the same few frontier models, the same language of co-pilots, the same promise of productivity. Over time, some of that interface layer will compress. If every product has a competent AI assistant, the assistant itself may stop being the differentiator. Then the question becomes, who can run it cheaper, faster, more privately, more reliably, and at larger scale? That question points down the stack. to the cloud provider with the lowest inference cost, to the chip supplier whose platform has the best token economics, to the foundry with capacity at advanced nodes, to the memory supplier exposed to HBM demand, to the networking layer that can make clusters behave like one machine, to the power equipment supplier sitting in the path of grid upgrades, to the utility with load growth, if regulators allow it and customers pay, to the cooling and construction firms that can help turn capital into working capacity. There is a historical pattern here, but use it carefully. In many technology waves, the early excitement concentrates on the application everyone can see. Then, as the application layer fills with competitors, value often shifts toward control points, distribution, platforms, payments, infrastructure, supply chains, operating systems, app stores, cloud providers. AI may follow a version of that pattern, but with a heavier physical base. The control point may not just be an app store or an API. It may be a cluster, a power contract, a packaging allocation, a region with spare grid capacity, a custom inference chip that lowers unit cost by enough to change pricing. A balance sheet that can spend before demand is fully proven. That is why the stock market ripple is broader than the obvious AI names. The market is not only asking who has the best model, it is asking who sells the picks and shovels, who owns the land, who wires the mine, who powers it, who cools it, who finances it, and who gets blamed when the neighbors show up at the zoning meeting. But this is also where the simple bull case can get lazy. AI demand up, infrastructure stocks up, is too clean. A lot can break the chain. Overbuild can happen. Margins can compress. Export controls can change demand. Supply chains can clog. Depreciation can rise. Local opposition can slow projects. Power scarcity can delay sites. Customer concentration can create risk. A model efficiency breakthrough can reduce expected compute intensity, or the market can simply price in perfection, which is Wall Street's preferred way of making a good story dangerous. So the stock trend segment should not be a victory lap. It should be a map of expectations. The useful market question is not which ticker wins. It is, where is the market assigning scarcity? In this cycle, the answer appears to be across the AI infrastructure chain. Accelerators, memory, foundry capacity, packaging, networking, cloud platforms, data centers, power equipment, utilities, cooling, and energy procurement. That does not mean every company in those categories wins. It means the market understands that the AI service layer depends on physical constraints below it. And that is the real signal. The more AI becomes a default feature, the more the invisible machinery matters. That is also the risk. If invisible machinery becomes the thesis, investors can overpay for anything that sounds like machinery. Not every power company is an AI winner. Not every data center project has good economics. Not every custom chip beats buying from NVIDIA. Not every cloud provider can turn CapEx into high-return growth. Not every supplier with AI exposure has pricing power. The chain can be real and still produce uneven outcomes, so the useful market read is disciplined. Follow the dollars, but also follow the constraints. Revenue mix, CapEx, lease commitments, power availability, customer concentration, margin pressure, depreciation, regulatory risk, construction timelines, supply commitments. Those are the signals that matter more than the chart line by itself. The story hiding underneath the AI headlines is not just that models are getting smarter. It is that intelligence is becoming an infrastructure product. The chip matters. The data center matters. The grid matters. The permit matters. The balance sheet matters. And the market is trying to work out which of those bottlenecks can actually capture value. So when the next model launches, watch the demo, but also watch the supply chain behind it. Watch who has capacity, who has power, who has packaging, who has permission to build, and who can turn all of that into cheaper inference. Because the next AI breakthrough might arrive as a paper, but it will ship through a rack, and it may wait on a substation. If this helped you cut through the noise, subscribe to Depth and Signal. The next episode will follow the part of the AI story most headlines skip.